Here's an example of how we used Fourier transforms a few years ago in a device that I patented with my research student George Flathers. At the time, we had a major mine collapse. Got the surface of the Earth over here, and they're deep underground. And by deep underground, we're talking about more than 1,000 feet underground. There's a mine. And it suffers a collapse. Here's the rock showing the collapse. We've got a miner that's trapped and is very unhappy deep underground because he or she knows that the amount of air that's available is declining rapidly. And it's not just that the oxygen's going down, it's that it's being replaced by methane that's seeping out through the pores of the earth. So that miner tries to somehow contact the top, but they can't. Landlines are destroyed by the force of this collapse. And if you've ever driven in a tunnel and experienced the immediate loss of all radio frequency communications, you know radio doesn't penetrate the earth well at all. The current guidance for miners is to take something metal and slam it against a rock hard and hope that that sound makes it through the top. The trouble is that sound, X of t, suffers from severe attenuation and also noise. And by severe attenuation, we're talking about less than 1 part in 100,000 manages to make it up to the surface of a 1,000-foot mine. The amount of noise caused by a leaf dropping from a tree 10 feet away from where you're listening is much, much greater than the amount of noise that this miner can generate through 1,000 feet. So our idea was not to generate impulsive noise, but rather to generate a perfect cosine, which turns out to be very easy to generate using a microcontroller. So we've got this perfect sine wave. Now in the time domain, of course, the sine wave looks squiggly. But in the frequency domain, it looks like two impulses at whatever frequency you're broadcasting, positive and negative. And that would be what you would get if you were broadcasting your cosine of omega naught t forever. But you don't want to have your miner wait down there forever. So instead, he's going to broadcast that cosine of omega naught t for some shorter period of time. Let's say it's going to be for 10 seconds. Well, that looks mathematically like you're multiplying in the time domain a cosine of omega naught by this top hat. Maybe it goes from minus 5 seconds to plus 5 seconds. So that's a 10-second long broadcast. But in the frequency domain, multiplying by a top hat is the same thing as convolving by a sinc. So that sinc function might look something like this. And you know enough about convolution to do this convolution in your head. Convolution by an impulse doesn't change the thing being involved. In the time domain, that's like multiplying by 1. So convolving this by this leftmost impulse will give us a received signal in the frequency domain. We're still working in the frequency domain here. That looks like this. Similarly, convolving by the right signal will give us something that looks like that. And this will be centered at our omega naught and our minus omega naught. So in frequency, in the Fourier transform domain, we see two peaks. If I was a better artist, these would be symmetric, that are centered at omega naught. Now what happens as time goes on? As time goes on, this becomes broader and broader. And as our top hat becomes broader and broader, our sinc becomes taller and narrower. And so after maybe 20 seconds, instead of it looking like this in the frequency domain, we get a much tighter peak here and a much tighter peak here. And if we were to do that for still longer, for maybe 100 seconds or 2 minutes, this peak now becomes too long to draw in the space that I've got on the board. This peak becomes really tall and really narrow. In fact, it starts to approximate a impulse, which is exactly what this top hat would become in the limit as it goes to infinity. And now when you convolve this by these two impulses, we get something that approximates, pops way up there, and it approximates in the limit as our top hat goes to infinity, 2 impulses. The significance of this is that maybe you can't detect your minors after 5 seconds or 10 seconds, but you just wait for a long enough amount of time, and those narrow, thin peaks at omega naught and at minus omega naught become arbitrarily large. Eventually they'll become larger than your attenuation, and they'll become larger than your surrounding noise, and you can spot them. I'm going to show you our device working in an actual mine on actual data. This was on a 890-foot deep mine, and we were sending a 71 hertz tone. If you're curious about how we created the tone, we took a speaker, the same type of large speakers used to transmit deep bass frequencies in cars that you can hear from across the parking lot. And those deep bass frequencies are perfect to transduct through the Earth's surface. So just like you can hear it through a parking lot, you can sense it using Fourier transforms through 890 feet. You can't hear it if you put your ear against the dirt, but after a few seconds of simulation, you can spot it. This is what our device looked like. And here it is reading the actual data that we read out a few years ago in the mine. So at first, we see a large peak right here. Turns out that that peak is not our signal. That peak is because we are receiving our signal near a functioning mine. It has massive amounts of electric power, and this is a peak corresponding to the synchronous frequency of that electric power. But as we continued to collect, we started to see another peak forming, lower right here. Now we had pre-selected one of 10 possible frequencies shown by these blue lines at which we were going to transmit. So any synchronous source of noise, synchronous meaning repeating, like those electric lines running right overhead, we're creating a much larger form of noise that the Fourier transform was identifying. But because it didn't fall in one of those 10 pre-selected peaks, we know it wasn't real data. Here's our real data. And over time it grows relative to the surrounding noise. Now, of course, the synchronous noise also grows, and it grows much faster than our signal. Our signal is very, very small, but the point is we can spot that we're broadcasting right here. And because this is a linear process, if we had 2 different groups that were trapped under the mine at the same time, and they were transmitting different frequencies, we could see these 2 different frequencies grow, and they wouldn't interfere with each other. Based upon this data and others, the National Mine Safety and Health Administration approved our devices for use in mines, and we sold the patent and the technology to Stratacorp, which is the world's largest manufacturer of mine safety equipment.